Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward. Here we are.
Here we are.
I just got back from vacation, so I haven't thought about anything technical in a while. This is our first episode in a long time with just you and me.
It is. It is. We've been interviewing people, which is great. But in the meantime, ideas and questions and puzzles have been backing up.
Brewing. Queue building.
Yeah, because I think it was in April you sent me a link to an article which talked about, it was saying that when Simula was created, the inheritance, so Simula was basically the first object-oriented language, and inheritance was actually like a performance hack, or it was a hack for both. Yeah, just in general, a performance hack. But
it didn't have the reasons that it does now.
It doesn't. And so, this article kind of blew my mind, because it's like, wow, is that true that we started with this hack and then people started going, oh, how could this be useful and meaningful? Inheritance sounds kind of mathematical, so maybe there's a way to... And
it's like the real world. You've got animals, and then you've got a cat and a dog, and
right.
It just models the real world so well.
Right. And see, when I went into it, I thought, oh, well, somebody before me had come up with these things. And I mean, I really didn't, I remember Smalltalk coming out, but I didn't do anything with it. I was, working with C and stuff at the time. And then by the time I started working with C++ and figuring out how dynamic binding works, and then why would you do that? And obviously, so we can have this inheritance hierarchy and it has meaning in the real world. And, there are books on domain-driven design that, works on mapping, one to the other. And it all made sense. But this article sort of suggests that all of this stuff was after the fact. It's like, oh, well, let's make up meaning for this. I mean, that's a little crude.
A lot of the OO stuff is...
a lot of the OO stuff, and maybe just a lot of stuff in programming in general. I mean, if you look back at the history and,
we do this because, but how often do we look back and see, is that true?
Yeah, is that true? And what was it? I mean, like if you look at Pascal, where they had, and this was actually my first encounter with this kind of thinking, was that they said, or at least it was taught to me, that the reason that you had to declare all of your variables in a declaration block was because it was good programming practice.
That's right.
And
it
then
turns out it was just lazy compiler.
It was lazy compiler things. It's like, it's way easier to decide how much to allocate on the stack when you enter this function. If everything is defined at the beginning, it's just way easier. Yeah. But it was easier for the compiler writer and not for the. Yeah. But then
it was
presented to me, and I think the professor or whoever was doing the presenting didn't know.
Yeah. And so they didn't question.
They didn't question. And how many things didn't we question? So then Smalltalk comes along, and it was just, really just recently I started thinking along these terms, which is that, so when you look at Smalltalk, its real benefit was you had this massive library of and you wanted to do something, you go, oh, this, mouse object does a bunch of things that I need. So I'll inherit from the mouse object and I'll make a cell, something that could be completely different, but it does what you need. And it's not really, you're never going to treat it like a mouse object. It just has some functionality that you're using. And then, and it's all dynamic. So you send a message. The fellow who created, I think it was Smalltalk, he created, and he said, I'm sorry that I didn't call this, message-oriented programming or anything, because the object wasn't the important thing. It was the sending the message.
Well, and the thing that is at least I think, is primary to objects is hierarchical structures. It's the polymorphism.
That's what we've been taught.
Using, and what's the specific name of that polymorphism? Because there's different types of polymorphism. Anyways, there's a word. There's a name for the hierarchical extension kind of based way of doing polymorphism.
So here's the story in my head. Smalltalk came along, did everything dynamically. So when you run a Smalltalk program, you send a message to an object. Object decides, can it deal with that message at runtime, all dynamically. If it can't, it sends you something back. It says method not found. Then it's up to you to figure out what to do.
Yeah.
Everything's dynamic, and you could build systems really quickly this way, but they were unreliable because you never knew when something was going to fail at runtime because
no way to pre-validate that what you were trying to do is actually something possible.
Exactly. And the same thing happens with Python. Unless you have a way to test every path, you don't know whether that path is valid, whether it's going to produce something valid because it's all dynamic and, very powerful for doing certain types of programming. Maybe let's say where you don't really care. Like you're dealing with big data, and if it fails, you go in and you figure out what's wrong and you keep going, but you can move forward at this really fast pace and get the results you need, et cetera, et cetera. But when you come back from vacation and you have 40 updates for your phone, all of which are bugs, you're going, maybe something's wrong.
Maybe something
here.
Foundationally is wrong.
So my story continues. It's like, Smalltalk does all this stuff and everybody thinks, wow, this is super powerful. We can build systems really quickly with it, but they're not reliable. So we go, we'll fix that by shoehorning types into an object-oriented language, which we did in C++ and Java, etc. So we went on, we go, types will fix it. And the problem is that I think we see this problem in the Liskov substitution principle. So
what's that?
So the Liskov substitution principle says any derived type must be substitutable for the base type.
Okay.
And because of that, the derived type can only use the functions, the methods, the member functions, et cetera, that are defined in the base type. It can't expand on it. Now look at that in comparison.
It's not like you can't upcast?
Well, you could or you can. I mean, and then you're tasked with making sure that everything is good. And we've seen like with sealed classes, we've seen that kind of making upcasting less less dangerous or even safe.
I mean, if it is, if your compiler knows about all the possible things that you can upcast to, then the compiler can say, you need to pattern match. You missed one,
right?
And and so that's where ADTs are.
Yeah, and I mean, when we were writing Atomic Kotlin, Svetlana and I had a struggle around this because I was going, no, upcasting is always got this open-endedness to it, and she had to keep coming back and going, no, it's actually because we have sealed classes. And it took a while for that to get through my head, but then I go, okay, but it still seems like so now with a mechanism like that, you can more safely add functionality like you do with Smalltalk. But it's still, doesn't it feel a little, what is this type? I mean, you're still figuring out types at runtime. So it seems like it's got some limits compared to what we're trying to do with, reliability.
Yeah.
So, my point was that the Liskov substitution principle is kind of diametrically opposed to at least the Smalltalk benefits of object-oriented programming.
Yeah.
It says, well, sure, but, you can't add functions. And that's always felt a little weird to me. And it's always been a little hard to explain.
Yeah.
And now I'm going, oh, this is
How did we get here?
How did we get here? And I think it was because
did we get to the wrong place?
Did we get to the wrong place? Because we started with, oh, look how powerful we can be with this. And then we discovered that with that power comes unreliability. And so we'll force types, we'll fix it, we'll force them in, and then we end up with the substitution principle. And now we have this like, wait, what am I supposed to do when I'm designing an object system here? And is this even sensible? I don't know. And maybe the answer is no. But in addition to that, I wonder, because we had this kind of backlash in the last, 10 years. People go, oh, objects were a mistake, pointless, and we should never think about them again. And I'm thinking, well, I don't personally, and most of my experience with this kind of thing is programming in Python, where mostly I start with functions, I use functions, they solve my problem. And then every once in a while, something gets really messy. And it takes me a while to realize, oh, if I make this an object, it solves the problem. But it doesn't mean that I make everything an object. It's not the Java approach to thing. Or, I suppose you could say Smalltalk, but Smalltalk doesn't have the type constraints that Java does. And so Java kind of ended up being not the worst of all worlds. Obviously, we produce a lot of things. We produce a lot of things with PHP.
That's right.
So,
it may not be the best way to judge it.
Yeah. I don't even know. It's like, because people always come back and say, well, I can get this thing to work in PHP. I can get things to work in Python.
Right.
They're not necessarily the kind of reliability that I want to deliver to, the end user, so that I don't have to constantly be doing bug fixes.
Yeah.
I don't know. It's just, so anyway, that's kind of what's been spinning in my head.
Yeah.
Just like,
one of the nice things that I've realized about objects lately, and I think it was actually John DeGoes had said something along these lines, but when you have an object and you know what it actually is, then you should be able to know what you can do on that thing. And this is where you're saying, like with Smalltalk, you could do anything. Like it was
you can send any message to any object, and it can go, I don't know.
And now in most modern OO, you hit dot in your IDE, and it tells you exactly what the options are.
Even Python, if you're using static typing.
Yep. Yeah.
Mm-hmm.
And with static typing, it is exactly what the options are.
Mm-hmm.
When I'm in IntelliJ, which is amazing and I love it, when I'm doing JavaScript in IntelliJ, I hit dot, and the list is like a million things long of things I can do. Some portion of those options is probably valid and some portion is invalid, just because JavaScript, it just doesn't know. But the ability to either go to an API doc, or I think we used to go to API docs. Now we just hit dot in our IDE. But the ability to have an exact verifiable list of things that you can do on that object is, for me, huge productivity gains, because now just hit dot, get the exact list of options. I see what the parameters are, see what the outputs are, and
you can guess.
That has amazing value. Yeah, and then from there you can guess. Okay, this is kind of what I want to do now with this thing, and so then you start filtering through the list to find.
And doesn't that show how important naming is? Because if this
Absolutely.
is our mode of programming, guessing is what we do, and boy, that name would be really nice if the name
matches
meaningful,
with the mental model that I have for what I'm trying to do. So if I'm trying to filter a list, it's great if the method on that thing is called filter instead of, I don't know, I'm sure you could think of a lot of other names for filter, but filter is the name that comes to mind for me. So I'm glad that filter is what's chosen there. It's a weird one, is like like map, I think is a pretty good name because it is a mapping from one type to another type. But flat map, this is the one we keep struggling with, is like flat map isn't necessarily a great name for what the operation actually is.
Yeah, it's literally what it does,
Yeah.
not the meaning.
Yeah.
It would be nice if
but no one really knows the meaning on that one, so that's probably why we don't have a good name for it.
Because I think at one point there was, I feel like there was an apply, which was like map.
Yeah.
And maybe that was in Python. I'm not sure, but anyway, it's like, oh, apply is probably a better choice than map.
Mm-hmm.
But map does suggest applying to more than one thing, whereas apply sounds like you're doing just a single thing. Yeah. So it's like,
yeah, I mean, in some ways, flat map should really probably just be called map. It's just that it can't be because the I don't think you can generally overload. Maybe you can't. Yeah, maybe it would work as just map. Because I think the overloading would only be on the parameters, not on the return type.
Yeah, you can't. Well, traditionally, most languages you can't overload on return type.
Yeah,
you can have covariant return types, but you can't. So the return type changes with the inheritance hierarchy. Yeah. So, if you have an animal, it returns an animal. If you have a cat, it returns a cat. So, that's the idea of covariant return types. But
so I wonder it'd be better if flat map was just called map and it just took a different function parameter type or something, because it really is just a map. It's just that the function that you take has a different return parameter.
Yeah, I think it was. I mean, now that, at some point in the future, we'll just be going, I want to apply this thing and I want to get the result out. And don't bother me with the fact that it's flat or not. Just do the right thing. Yeah.
I guess in the case of flat map, at least it has the name map in it. Yeah. Whereas there are some other names that are used for that monadic functor. Mm-hmm. What some of the other names for it are, but there are definitely other programming languages use terms other than flat map. Mm-hmm. What really drives me crazy is some APIs, like the Apache Spark API, mm-hmm. has a flat map on it, and I think this is also true in a few places in Kotlin that I've found. But the types of the flat map function are not at all what they should be to be like an actual flat map. And it's so annoying when you encounter a flat map that is not really a flat map because the function parameters are not what they should be to be a flat map.
Yeah, that sounds disappointing.
Yeah. It's like you're hoping to use it as a monadic operator, and then all of a sudden it's like, oh, the types are not what you need to be a monadic type.
I started reading this book. Let's see. It's the Functional Programming in Scala by Chiusano and Bjorn.
Paul and Runar, yeah.
Yes.
Who have both gone on to create the Unison programming language.
Really?
Yeah.
Oh.
So I don't know totally what their history is, and we need to just have them on the show sometime. But
there we go.
But they I think discovered a lot of important things about functional programming and FPOO
in the process of writing that book, maybe.
Yeah, and just on their own journey in Scala, and I from what I've seen of them, it seems like that was a stepping stone to there's some foundational things here that we need to just go fix at the foundation to make this better, and that was.
Is it just Unison. The two of them working on Unison, or is there?
They're the two primary ones that I know of, but there may be others as well.
Okay,
so I only know all this through watching a few talks and following them on Twitter.
Well, so the reason I'm going through it is to try and increase my clarity, but also to see how we can achieve what we're trying to achieve with our book. And But one of the things I came across was I found myself going, why are all of these functions inside of classes or objects? Why are they doing that? That's dumb. Why are they doing that? And I said, wait a minute, did Scala require that like Java did in Scala 2? And Bill goes, yeah, they did. And I'm going, yeah, it's probably something I should have remembered, but it's just like after working with Kotlin,
Yeah.
well, and for that matter, Python and C++, where you always had top level functions. It's like, it's so weird to see this artificial constraint that functions have to go inside of classes or objects.
Yeah.
It's just, yeah, but fortunately Scala 3 took the hint and fixed that.
Yeah.
But for a language that is saying, we're all about functional programming, but you still have to put your functions inside of classes like Java. It was weird.
Yeah, that's weird.
Yeah. In hindsight, it was weird. I mean, at the time, it was like, oh yeah, you're doing this because Java did it. Yeah. It's another one of those explanations that don't actually hold very well.
Yeah.
Well, plus I know that they had to go through some artificial things in order to have top level functions, and ultimately they ended up putting them inside of classes as far as the JVM was concerned. But I don't have to look at that and be confused by it. Because, when you see something inside of a class or an object, you're going, you're doing this for a reason, right? What would that be?
Yeah.
And like, not just a arbitrary constraint reason, but a design reason. And then you have to figure out, oh no, it's not a design. It's so easy for your brain to get cluttered up with stuff like that.
Yeah.
So.
Yeah. Back to your kind of initial question about like, mm-hmm. It seems like it was just initially about performance improvement. Mm-hmm. It was like the way to get a performance improvement, and we've evolved many possible mythologies about why object-oriented programming is valuable, and now we're maybe as an industry beginning to reevaluate some of that. Mm-hmm. It's going to be interesting to see like where this all goes. But one of the things I've been thinking about related to this is that we functional OO, I think, is helped move us forward into some very important things. But I think that as we go further into this, we realize, okay, there's something else kind of foundationally wrong with even functional stuff. A lot of, maybe not some functional stuff, in that when we call a function that talks to the outside world, that becomes a place where we can have unexpected failure, unexpected something, state that is changing unexpectedly. That gives us indeterminacy. And what our book that we're working on is really focused on is, okay, functional O is great. That's a step forward. Effect-oriented programming is the way that you can have a lot more determinacy in your system by isolating that talking to the outside world. And so I think that, I did functional OO for a long time in Scala without doing effects. Mm-hmm. And it took me a step forward, but I think that there's even another step. And I think that there are other ways to solve the problem too. I think that Unison doesn't do effects. I think it uses something called algebraic effects, which are different than like monadic effects, which is we're focused with Zio on monadic effects. But I think there is other approaches to solve this problem. But yeah, so I think that's going to be interesting to see like how kind of the programming world kind of steps through. Objects. They don't really solve some foundational problems that we have. You and I were talking earlier about the combinatorial issues with, I've got a bug in one function and a bug in another function and a bug in another function. Like we just like accumulate.
And they multiply. They don't just add.
Yeah.
Yeah. And it's like, finding them for one thing. because you could write a unit test that might find the first bug but not the others.
Yep.
Yeah, and when you start looking at, well, functional programming is filled with these tiny little functions that do very little, but they're pure functions, and because of that, you can combine them safely. But if something has bugs in it and you start combining it, you get this effect, which reminds me of concurrency. It's like, oh, well, yeah, in the small, like the people who write the operating systems, they can use locks and threads at that level, but what they're doing is kept in a little tiny box, and so they can see everything. But as soon as it starts getting bigger and crossing boundaries and things like that, then it becomes unmanageable. But the person who wrote the thing inside the little box isn't aware of that. It's like when exceptions were introduced, you look at it in the small and you go, wow, this is cool. I just throw an exception and it gets taken care of. It gets caught here and taken care of. Great. And then when you start scaling it up,
you get to a level of complexity where it falls apart.
It's unmanageable. Right. And yet it's real easy to fall into that variation of what I keep calling the simplicity bias. You're going, it works here. Or we were talking about, when you how you agree on things, consensus. So we were talking about consensus, and I had struggled with this for a long time, like, because I went from, oh yeah, consensus, that's great, to my own experience with it, which, oh no, it's it's unmanageable. But when you add that extra dimension of scale, you go, oh, well, you, me, Bill, and Wyatt, we can pretty easily work through things and agree on things. But now, what happens when we double, triple, when we add a lot of people, then consensus starts to break down. And it's like, oh, okay. When the people who designed Go, there was like 3 of them or whatever, and they could just hash everything out among themselves and they could just do a consensus model. But if on a corporate level, you've got everybody's bike shedding every feature, and it just totally breaks down.
It's a model that works in the small but not in the large.
Yeah, exactly. And I mean, I think a lot of these things are like that. We do this.
Concurrencies are obviously a super interesting one.
Mm-hmm.
Where this was not even that long ago, where I got bit by, it's like some Java API, like date time formatters, like something like
should work by now.
Right. And I totally had a bug where it was not expressed through the programming model that this thing was not thread safe. And so I was calling it from multiple threads, and sure enough, it was not giving me the expected results. And I'm like, something foundationally wrong with the model if I have to think about those things.
Oh, right.
And if I can even have bugs from those things.
I don't know, this is a couple of years ago, I'm sure, when I was working on the Java 8 book, and I kept coming across this assertion that one of the great things about constructors was that they were thread safe. And I had repeated this myself, because I think in C++ it is true. So, the constructor happens and you get the thing back and you can't mess with it nothing can mess with it while the constructor is happening. And everywhere I looked, people go, yep, that's it. They were all echoing the same thing. And I decided, I better sit down and figure this out. And I showed that, yes, the constructor in Java is not thread safe. And so all of these things, the whole model, clearly they just threw it in, Gosling and those guys just they go, oh, we should have threading. Let's just throw this in. We don't need to worry about it. It'll just work. I don't know. And then it's just been one thing after another, and they had to deprecate most of the thread API and everything. There was that thing where, okay, you can write this library and it works great for you, but it's not thread safe. And to make it thread safe, you have to do what?
Synchronized or
something. You have to jump through a bunch of hoops. And you're
in,
going,
in the right places.
I'm not trying to solve that problem right now. I'll just put the library out there.
Yeah.
And then somebody uses it and discovers, oh, this isn't thread safe. And it's like, oh my gosh.
Yeah.
And there's so many things like that.
Yeah. Well, and there's things that are, I think maybe part of what our big point in our podcast is that the things that can bite you in programming shouldn't just be notes in documentation. The programming model should actually tell you this is going to bite you. And then you have to, as the programmer, it's right in your face. And ideally your program won't compile unless you've dealt with the things that can bite you correctly, whether it's concurrency, whether it's exception, error handling, whether it's whatever.
Mm-hmm.
And I think that we're evolving to that, but we have to rethink a lot of foundations to get there.
Yeah, because it was just kind of thrown in as an ad hoc thing. I mean, if you were going to have this messy threading system that Java put in, it should be like, okay, look, you either have to annotate, you have to put something in here that says, I have explicitly decided not to make this thread safe. So if you use it in a program that's got threads, you get warning, something jumps out at you rather than it's just, oh, you have to be skilled at this.
Right. You have to, what likely happens, what happened to me with that formatter example or whatever it was I had to hit a bug, debug my program, realize that I had hit something that was not thread safe. And then, of course, after banging my head against my desk for a while and I actually read the documentation, this is not thread safe. I'm like, yeah. And now I know, because
that needs to be part of the type of that thing.
Right.
It's like, some information embedded in it that says, boink, not thread safe.
Exactly.
And warning.
The threading, the things that can bite you from threading need to be expressed through the type system, through the compiler, through something that
doesn't just slip past you.
That's right.
Yeah, because you go, oh, look, I got, it printed something out. It's okay.
Yeah.
Yeah.
Yeah. Exceptions are the same exact way. It's like, except for checked exceptions, it's like, how do you know how this thing's going to fail? Oh, I don't. It just can fail in all sorts of different ways. Null safety is the same as well. Yeah.
It's feels like we're. I think in the future they're going to look at this whole period and say, "Oh yeah, they were just thrashing around trying to figure things out, and they went down all these blind alleys."
Yeah.
And they went way far down the blind alleys before things got.
In the case of they went really far down.
Really far down. No, it is the solution. It works so well in small talk. Yeah.
Yeah. I don't write very much OO code anymore. I mean, I use, I think, some key pieces of OO that are important, like being able to put things into packages, like that, just for an organizational aspect, that's useful. But
is that OO? Putting things into packages isn't necessarily OO. I mean, like,
I think if you take a pure functional, like a Lisp or something like that, then there is no way to like
packages mean more,
like organize in that way.
Well, but Python's that way. It's had packages from basically the beginning. So even if you name the package, it says, oh, well, the file name becomes the package.
Yeah. I would say that it's kind of an OO construct of being able to organize in that way. Another one is to be able to like dot operate on a thing. Whereas I think in pure functional, you can't dot operate on something because there is nothing that isn't an object.
There's nothing to.
It's so what you always do is you always have all your functions and you pass your
all arguments
value to a function. And so instead of doing dot operations, you're always doing that inverted way, which I don't like program. I like dot. And I think that part of it is what we were talking about earlier, which is my IDE can tell me, here are all the things that you can do on that thing. And so I get some
Right. You have a thing you're starting with, and you go, what do I want to do to this thing?
Yeah, exactly.
So I can put a dot and it drops down a list.
Without, so I would say that's an OO construct that is important to how I program.
Right. Whereas if it was just arguments, how would you would say, oh, well, I have this argument. What function would I pass it to? It's like, well, how would the IDE give you that?
I mean, I guess it could look through the method signatures of or function signatures of all your functions that are possible. And,
in the library functions.
Yeah. It just seems a little unwieldy.
Yeah. And it's harder to think about it that way.
Yeah. Yes. For me, it's inverted, but I know a lot of people program in that style and like it.
Uh-huh.
But so I think there are definitely things from OO that I use, but polymorphism, that hierarchical inheritance, I don't think I ever really use that anymore. I use ADTs, so all the time I use ADTs, sometimes in product types, but I do not
algebraic data types.
So being able to combine different values into a named thing. So that's a product type, which is in Scala a case class or data class in Kotlin. And then a sum type, which is something that can be a foo or a bar.
So we use the pipe between it.
That's one way to do that. Okay. That sum type. The more classic way in Scala is a sealed trait, which in Kotlin is a sealed class or something, right?
But they didn't have. I mean, Scala 2 didn't have ADTs, so
you could do a sum type. It kind of did.
It just didn't have the nice syntax.
In Scala 3, it has a different way to do them. Yeah. But in Scala 2, you could do product types through case classes, and you could do sum types through sealed traits. So you could definitely do it,
right?
And then you get exhaustive pattern matching on the sealed traits, and
yeah, I have to say being able to say this or this or this as a type fits pretty easily into my head. It's like, oh yeah, that's what I want to do. Yeah. And then having the type system watch over all that stuff. Yeah. That's all pretty appealing.
Yeah.
And there are still situations where I do use polymorphism. But that demand that these things all have this common interface.
Well, and there's other ways to do it. Like now with extension methods, that's another way to attach behaviors onto things.
Right.
And then type classes. We've done a number of explorations into type classes, which is called ad hoc polymorphism. Parametric polymorphism.
With generics.
Yeah, generics. So there are other ways to achieve the similar goal than just inheritance based.
I spent so much time trying to fit the inheritance peg into a hole that I don't yet easily have the big picture of, oh, this is polymorphism on a big scale, and here are maybe the different places where you would use it. Yeah, the different strategies. And can we replace inheritance-based polymorphism with all the rest of those things?
Well, and what's interesting is in Java, inheritance-based polymorphism is kind of the only... Well, I guess there's parametric polymorphism.
Yeah, they have generics, which they added later, yeah.
Yeah. But I think a lot of my issues with Java are because there is a limited number of ways to achieve the reusability goals, and so we do jam inheritance into a lot of places where if you can look at it from a different way, you're like, yeah. If we had some different tools and some different strategies, we probably would not be in the crap that we're in this terrible programming model, because we would have solved this problem in a different way. But in Java, we just shove inheritance everywhere.
Well, because that's what Smalltalk did, and they were modeling it after Smalltalk. But then when you look at generics, you go, oh, that was another. Because it's like if Smalltalk is like, yeah, you got a bunch of objects, you send messages to them. There are no constraints on what message you send, and then we have, oh, well, they have to be inherited from the same type to be able to use them using the Liskov substitution principle. But then the generics is another way to deal with that. Oh, we can't have the Wild West of Smalltalk, so we have to batten it down. We can only batten it down so far this one way, so we have to add generics to do the other way. So that's that sort of supports my hypothesis that we're backfilling from a model that wasn't actually. We were trying to put constraints on it, and my argument is that the constraints were because of reliability, and so far I'm not talked out of that. And what we're trying to do with the book is we're focusing on the reliability aspect of things. I mean, that's our motivation. It's like, why are we doing this? More reliable code. And I think everybody can relate to that. And ideally being able to put systems together faster, whether we'll ever reach the speed that Smalltalk achieved is another question. But Smalltalk didn't have the reliability constraint. So, and it's, I mean, I don't think we can keep going forward. I think it's limiting the size and complexity of our systems too. It's like, well, if you can't build a reliable system, building a big system that's not reliable is not really solving your problem. And then we're going back and finding bugs one at a time. Whack-a-moling our way to, but we never have a reasonable sense that it's reliable. We never know that it's like we go, oh yeah, this is.
Are we getting better, or
are we just adding more bugs while we're fixing these others? It's and testing is sure important, but it doesn't seem like we've been able to solve. I mean, just teaching people to write tests has been this, much bigger hurdle than we ever thought it. I think we thought, oh, well, this is obvious. You got to test your code. You got to test it so many ways that it'll give you a reliable system.
There's been so much energy put into making testing more extensive, making it easier, making it better, whatever. So much energy. And what we haven't done a lot of time looking at is, what are the reasons why we have to do so much testing to have reliable software? And is this a sustainable model, or do we just need to change fundamentally how we build some things so that we can get reliability through better reliability through other mechanisms? And
building up from small pieces that are guaranteed reliable.
I know there was this huge debate around types versus tests, and and I remember a presentation from somebody who is a big Ruby fan, and they put so much emphasis onto testing, and it's like, oh, how do you validate this?
Because Ruby is more dynamic than Python. It's like,
how do you validate that this thing is correct? Oh, you just write tests. You just write endless tests. And could you ever sufficiently write enough tests in a dynamic programming language, like to actually be able to have a level of validation?
Well, you just get 100% coverage.
That's it. It's so easy.
I'm being sarcastic.
And I look at it and I'm like, no. There's got to be better foundational models.
It's a Zeno's paradox. Zeno's paradox is, okay, you're standing across the room from a wall, and now we go halfway that distance, and we go halfway that distance, and you can never reach the wall, but because you keep having the distance. So it's this kind of asymptotic. So you can never completely, you can never really achieve 100% coverage. I mean, the coverage tools don't show you that because they have a different motivation, I think.
Yeah. Yeah, I mean, I even look at code coverage and I'm like, it's all built on a faulty model.
Yep. Absolutely it is. And then some manager says, well, just give me 100% coverage and then I'll know everything's good.
Yeah.
And you go, no, it doesn't tell you that.
Well, and so many of these things are predicated on the idea that our system never changes, that we never refactor, we never add new functionality. And so,
well, if nobody's using the system,
it's great.
Yeah.
Yeah.
If nobody uses the system, that's true.
Yeah.
But if anybody uses the system, they're going to say, I need this.
Yeah. Yeah. I mean, you're always adding new features, fixing bugs, and refactoring. Refactorability is such every code base I've ever worked on that wasn't just disposable, I was constantly refactoring it.
Mm-hmm.
And for me, type systems let me safely do refactoring and evolve a code base in a way that my tests don't burden me from doing that. In dynamic systems, refactoring is, you don't ever want to refactor your code because
you don't know what you're going to break.
You don't know what you're going to break. And then your tests break and you don't know why they broke. And it's what I do now is I refactor my typed code. And as soon as my code compiles, like, sweet, I've got a pretty darn good level of assurance that my big refactor that I just did, that this is going to work. But then I run my tests, and usually I have to also do some refactoring on my tests because I changed, something. But then refactor my tests, and then my tests pass, and I'm like, okay, I now have just as much confidence that this huge refactor that I just did, I have just as much confidence that it works as well now as it did before.
So when you do that, when you're writing, a functional system and you have tests still, do you find that you have fewer tests or
with functional systems?
Yeah.
With pure functions, yes. But really for me, the type system, a strong type system is the biggest factor in that. Pure functions help a lot because there's just so many less areas that can go wrong when you're in pure functions. But for me, the type system for me is a huge level of testing.
Mm-hmm.
And if it compiles, if I haven't sent a message to an object that it can't handle, the compiler tells me that. Mm-hmm. And so the type system gives me a lot of certainty around the reliability of my system. And then there is a level of unit tests that give me another level of usually around logic. Is this logic correct? And then the integration tests give me really that like final level of, okay, my integration tests also pass. And now I'm got pretty good certainty that there's very few bugs in what I'm about to.
I've built a reliable system. So when we add Zio into the mix, that presumably narrows the field of unreliability even further.
Yeah. Because we've made 99% of our system pure functions.
Mm-hmm.
And there's only this thin layer
we've isolated all of the weird variability into these boxes, which presumably Zio is somehow constraining and has ways to test and things like that.
Yeah.
Okay.
Yeah. The concurrency issues, exception failability issues, like all that stuff has been isolated into pieces that give me some strong guarantees around what can go wrong and the behavior that can bite me. Mm-hmm. And so we've isolated the places that can bite me into very specific spots, and I can test those in specific ways. So I think ultimately what I've done is I've increased the amount of my code base that can be actually tested with unit tests, because they're and I've also increased the areas where the type system gives me guarantees on on the types that I'm using. So yeah, for me it is a whole nother level of reliability and the ability to be sure that what I'm delivering is going to work in the way I expect it to.
It's very intriguing. I mean, I'm looking forward to seeing how this plays out. It's like I've got the basic framework starting to appear in my head, but and the motivations and everything, but to see how it actually works is going to be, and that's what we're trying to express in the book. Yeah.
It's a lot of fun. But for the future of OO, I think there are certainly some important things in OO, but inheritance for me it's gone at this point. Like, I don't need inheritance.
Yeah, that would be an interest. Maybe this is going to be an interesting example. Would be to start with an inheritance, I don't know, pets or shapes or something like that, and then show at least one alternative way to solve that problem without inheritance. I think that would be a very compelling. I don't know if that's a chapter or part of a chapter or something, but to show that, and ideally maybe in more than one way. Say, here's the way you can do it.
And in Scala 3, one of the annoying things is that we've got now 3, maybe 4 different ways to do sum types, to do ADT sum types, and that's I don't like that. There should be one way to define a sum type, and
one, and preferably only one way to do it. Yes, that's from the Zen of Python.
Scala definitely suffers from there being way too many ways to do things. So I'm not saying that Scala 3 is perfect. I think it is an improvement that it embraces ADTs as a core construct, but I think that languages like Unison have a chance at like getting a lot of this right, because they don't have the baggage that they have to bring along, and they don't have interoperability things to think about. There's just like, it's like if you're building a language on top of Java, you have to support inheritance. Like you probably just don't even have that option unless you just want to totally deviate from real compatibility.
Oh, right. Well, right. If it's a compatibility issue. Yeah. Well, right. So can we choose one, our favorite way to represent ADTs and just stick with that?
Where it's a little annoying in Scala 3 from what I've seen is that the new ADT sum types and product types are you get erasure on those. And so if the problem that you're dealing with is fine with erasure, then you can use that one. But if you need the type information, then you have to use the, I don't know if this all comes down to like boxing and unboxing, or, it's like, it's like the origin of OO. It's like we solve these problems, and then you're faced with, you put onto the programmer the onus of having to figure these things out. When should I do it this way? When should I do it this way? Because performance. And it would be nice to, like we've done in a lot of other places in programming, like immutability and whatever, is to be able to get to the point where performance is not the reason why we have to decide one approach or another. And with Scala and ADTs, where I think that in a lot of cases we still are, the programmer is still deciding the approach, and performance is one dimension to that decision.
Yeah, I know I've come across various ex post facto explanations for why erasure is a good thing, and I just, because coming from C++, where we didn't have or need erasure, you just, but yeah, that duplicates code, but that was never really it turned out that was never really a problem. But they even say that in explanations. I mean, I think I even read one that Brian Getz gave it at some point. And he goes, oh yeah, that would be too inefficient from a code generation standpoint. And like at first there was a concern in the C++ committee that using templates, which is their version of generics, where the compiler would generate a different piece of code for each type that you use. Oh, that would be too inefficient. But that nobody talks about that argument anymore, except in other languages where they go, oh, that would be too inefficient. But in C++, no. I mean, and if it is, you can always isolate, you can write a couple of functions and you can have the function that is using the specific type information be a very small piece. And so it doesn't, and so anytime somebody justifies erasure to me, that's where my brain goes. It's going, well, we didn't have to do it in C++, and you always knew what type you were dealing with inside of that function. You could do whatever that type supported. I was like, that was pretty nice.
Because reasons. And a lot of times in programming, those reasons are performance.
They're performance. Well, when you think about vars and vals, at least, well, like when I started, I was doing assembly language programming and we had very limited RAM. Yeah. That was expensive stuff. And it's like, you can't just
keep creating those
RAM and ROM. You couldn't, you had to reuse that memory. And so but then it just became part of the culture that you would have vars. And the idea of never using vars was like, no, how would you do that? Yeah. But you go back, oh yeah, that was probably another efficiency hack, possibly just like objects were. Who knows? I mean, I'm still mulling over that one article and, wondering about its impact, but it really does. It makes you wonder about the whole thing. And it's pretty interesting in hindsight. Yeah. But all that time that we spent, my gosh, I think you were too young to remember the cloud versus box wars. Oh, yeah. Do you remember those? Yeah. Yeah. And it was like, these guys were getting up on stage and using, what do you call it? Where you attack, ad hominem attacks, where you attack the person. Yeah. They were actually kind of, or at least bordering on that, going, well, you're stupid because you want clouds and you're dumb because you want to use boxes. Yeah. And there was going to be all of this stuff, and the object diagram was going to tell you everything. Well, and there's another example of objects not really working out, because it's like, we spent all this time figuring out how to do object diagrams, and we're going to have tools that would generate the diagrams. And then there were people who were convinced that we could take those tools and automatically generate the code. And they were, I remember
to a program.
So yeah, the automation of programs. And I remember somebody saying at a conference, yeah, we're 90% there. Well, that was 20 years ago. And it's like, oh my gosh, the number of times that I've heard 90% there and then nothing. Yeah. I mean, Perl 6, was it? How long has Perl 6 been 90%? Or maybe they did come out. Did Perl 6 actually come out to no fanfare at all, because everybody had already left it?
Yeah, I think self-driving is one of those, self-driving cars is one of those same things where it's like, oh, we're so close. But that last 20% will take us 1,000 years, to figure it out.
Well, or it'll need, I don't know, constant machine learning or something like that to be able to, because it's such a complex problem. And how can we survive unreliability issues? I mean, the thing is, I go I'm riding in a Tesla. We don't have it takes over so many of the functions. Well, I know the easy things, but the things that require human intervention and that we're bad at. And my God, I was in LA a few years ago, and we're on the freeway, and there's this big gap because this person is weaving back and forth across lanes, and finally getting way around and passing her, and she's like texting madly and doesn't no clue. It's like, well, the self-driving vehicle can take over, or the most common accident is rear-end collisions.
Yeah.
I mean, even the non-self-driving cars apparently have,
my car. It's not like full self-driving or anything, but
it keeps you from running in the car in front of it.
Exactly. It'll keep me from rear-ending.
Really, and so
which is a kind of basic problem.
It's a kind of basic problem that we've always had, and it's caused, how much, costs and everything, because somebody rear ends somebody and then the whole freeway comes to a stop.
Yeah.
And all of these things that it can do that take pressure off of the human to perform, which we're just not good at constantly. And it's stressful.
Make mistakes. And
it's super stressful. Yeah. Because, I mean, you make a little mistake and you could be dead or, you could, there's all these issues. So it can do all that stuff, and that's great. But whether it can be, what it takes to get 100% self-driving, can we do that with the current technology, that programming technology that we're using, or does it need to start from a different point, like perhaps what we're talking about in this book? And we will, I have no idea who's going to show up or whatever, but we're going to do a little weekend workshop before the Summer Tech Forum conference. And
on effect systems,
or if all we do is get to the point where people go, oh, I get what a monad is for and what it's about, or the basics of it, or whatever, I'll be happy. And then we'll have the process of trying to teach that as a feedback mechanism. And that's the 2 days before the conference. And that's part of, if you come to the conference, that's part of it. And we'll have to start, doing this so that we get this feedback to show us whether we're
that's right. It'll be a good
reaching people
mechanism.
It'd be nice to figure out how to start doing that on a regular basis, so that as we go, we think this chapter is good, and we try it out on people, and they go, I don't get it, and then we have to go back and
integration test our chapters.
Absolutely.
Through workshops.
Through workshops, that's the goal. So that's this August. And if you go to summertechforum.com, you will find everything about it. Including pictures of how gorgeous Crested Butte is in the summertime.
Flowers have just been amazing.
They have, and we'll be doing, hiking and mountain biking and possibly floating down the river. Who knows? We kind of figure these things out. But we have a good time. Always seems to be a way better time than a Eyes Forward conference.
For sure. All right.
Okay.
Well, hope to see you there. Thank you. Well, I'll see you there.
You will see me there.
Hope to see our audience there.
Yes, hope to see our audience there.